Hey everyone, welcome to the fourth video for Chapter 1 for Math 244. In this video we're going to be talking about two more theoretical concepts from differential equations, namely those of existence and uniqueness, and sort of discussing what they are, what they mean, and also kind of make a tie back to how they apply to mathematical models and things that you can actually do physical things with, even though, they might seem like theoretical, not applicable kind of things. We'll still talk about how you can do things with them and make sure they use them to verify that such model is good. Let's go ahead and get into that. So if we have a differential equation, there are two main questions we can sort of ask about it. We can ask about if there is a solution and if there is only one solution. So those are the ideas of existence and uniqueness. So the first of these that we'll talk about them both very briefly and then move on to sort of what they mean for physical systems, is the idea of existence. And this asks the question, is there a solution to my given ODE? And at the outset, this answer is not necessarily true. You could write ODEs where there's no solution, or at least there's no solution that extends forever. Say, you could write a solution that has like a finite time blowup. We'll talk about that in a couple weeks. But there are ways to have solutions that don't exist and don't do what you want them to do. The other question in the area is the idea of uniqueness. Is there only one solution to my ODE? I.e., are there not two different solutions that meet all of the conditions that I care about and still solve my problem? And both of these questions are very important from the mathematical point of view. So for instance, if you've heard of like the Millennium problems, one of them is to prove existence and uniqueness for the Navier-Stokes equations, which are used to mathematically model fluid flows in pipes or in other types of systems. And we being the math community, still don't know if those equations always have a solution and if there's always only one solution to the equations given certain initial data. We just don't know that question. And that's something that is obviously important. They're offering $1 million to anyone who can solve that. And so that's questions that people ask in the mathematical community about all the time. Now, the question is, with that, how does it apply to, engineers, physicists, people who don't necessarily want to solve this millennium problem, people who just care about using ODEs to model stuff? And the thing that it really helps with is it helps you verify if your model is valid. Because in nature, this happens, right? In nature, something happens, and given initial sets of data, only one thing can happen. Like the ball is going to drop out of the sky if you drop it. There is only one solution, and a solution is going to happen because, life moves forward, things are going to happen. So in nature, we have these two properties. So the question is, do our models also have them? Because, they should if we're going to have them model nature. Another thing to consider about this is this also helps us look at when our model starts to break down and when our models start to fall apart. So for instance, if you look later in the book, there's these existence and uniqueness theorems, and at certain points, based on what your ODE looks like, they're going to break down, and the theorem does no longer guarantees existence and uniqueness. So beyond that point, you probably shouldn't rely on that ODE to model your equation, because once this uniqueness breaks down, there's no guarantee that anything you actually get out of that solution is going to be helpful. So you'll see an example in one of the maple problems where you're trying to model population growth, and at some point the growth goes to infinity. At finite time, it blows up and goes to infinity. So really, you shouldn't look at a time anywhere beyond that for trying to get the population value, because it doesn't make any sense anymore, right? You've said the population is going to go to infinity and then come back down, none of which makes any actual physical sense in the case of the problem. So if your model has existing uniqueness that breaks down, it's important to know where that happens, to know how far you can push your model to sort of solving your problem and moving forward from there. So I'm kind of summing that up in the point that if your model has some problem where existing uniqueness breaks down somewhere, at that point you need to stop using the model. You can't push the model any further beyond that because you don't know anymore that your model is going to actually follow what's going on in the physical system once existing uniqueness breaks down. So that's why it's kind of important to, even in engineering and physics perspectives, still consider these existing uniqueness properties, because they are sort of what makes your model seem viable. And if they break down, your model is no longer viable and should start being ignored, either to, you have to stop at a certain time, or you have to find a better model to replace it that makes more sense. All right, that's basically what I wanted to say about this for this video. Thanks for watching. There's no video question for this one. It's just kind of a tangent on this, but we'll see more questions about this stuff as we get to like section 2.4, 2.8, which talk about these uniqueness theorems. We'll bring up more problems then and start talking about it in more detail then. So thanks a lot for watching, and I will see you in the next video.